Chapter 7, Section 5, Formulas, Applications, and Variations. We're going to look at formulas, direct variation, inverse variation, joint variation, and combined variation. Well, we run into a lot of formulas now, and a lot of this is we've dealt with formulas before, but now we're pushing this more into a function format again, and doing these things. And this first one is a relatively complex formula in the fact that you have to add fractions and those kinds of things. But this frequently, occurs. They're talking about that. In electronics, you can have a formula which is 1 over resistance equals the 1 over the resistor, resistance 1 and resistance 2, when they're talking about having two resistors basically in parallel circuits and those kinds of things. And if you're not familiar with electrical modeling, that I guess I can be a little bit weird, but they show diagrams in this way. So the total resistance here is this big R, but these are the two smaller resistances that run in parallel. In other words, if there's electricity passing through here, it's kind of like they take up both resistors at the same time. Well, this is the formula for that. And if we want to solve this and stuff, and the other thing that this note over here, student notes, says subscripts 1 and 2 in example 1 indicate that R sub 1 and R sub 2 are different variables representing similar quantities. Okay? Or basically they want to make sure that this little r means resistor, but you can have different resistors and they can have different values in a sense, indicating the amount of resistance that they're dealing with. So basically they start going through solving this stuff. So if I took this resistance stuff here where I got R of R1 R2 times 1 over this thing right here, which is basically clearing out, they're showing this in this form, is that they put in this new function. If we multiply both sides by the LCM of the denominator, basically they're solving this equation. And what they're trying to do is really clear the fractions. And we had that as a strategy, where the common denominator between least common denominator between all these fractions, which is this big R, R sub 1, R sub 2, they could be, this normally going back to other chapters, we could say this is Y and A and B, right? So you'd multiply both sides by that product of those three things, and what does it do? It clears the fractions. And basically deals with a equivalent equation, which means equivalent equations are, if I follow the rules of algebra, like I multiply both sides by exactly the same thing. Now why I chose that is I had a reason for that, was to clear the fractions, is as long as I follow the correct rules, I make sure that I take it times the entire side, so distribute over that, and so on. I have an equivalent equation that has exactly the same solutions. In other words, I haven't changed any possible solutions for this equation. So they take this now and they subtract r little r sub 1 from both sides. And boy, you can see you can get buried in this these variables and stuff like that. But don't get too freaked out about that. It's good to go through this. I kind of bit off a complex example because of the way these variables are represented, but this is a good thing to look at because you'll get bits and pieces of this all the time. So what do they do here? They have this new thing. They subtracted R, capital R sub 1 from both sides, and they end up with this, and then they decided to multiply, or to factor, excuse me. That's factoring using the distributive property. We got an R sub 1 and R sub 1 right here. Well, I can factor that out, and I end up with R sub 1 times the quantity of R sub 2 minus big R here, right? Capital R. Well, now if I wanted to solve for R sub 1, I would divide or take 1 over this whole thing, or take the, make this be 1 over and make this the denominator, the fraction, right? And that would make that go to 1. They don't show that entire thing. They call it, say, dividing both sides by R sub 2 minus R. I would usually say multiplying by both sides by the reciprocal of this, or multiply both sides by 1 over R sub 2 minus R. In that form, I tend to like it better that way. Thus, I can stay away from that division subtraction as much as possible. I can use a lot more properties to help me manipulate these equations and so on. So what they did is they basically solved, they created a formula to find out what one of the resistors is. Okay? And so if you put in these other values, you'd come out with what that resistor is. Now example 2 starts with formula in astronomy. This is to find a satellite's escape velocity, which is, how much velocity is this thing, how fast does this have to go to break away from Earth's gravitational pull, and that's what this formula does. And so they explain what that is. Escape velocity is a capital V. The planet's radius, where the radius is a planet's radius, is this R here. H is the satellite's height above the planet, and G is the planet's gravitational constant. In other words, we're not just talking about Earth here. Is if they were trying to make this satellite, let's say we had something circle around the moon, we could use this formula. It's going to have all the variables that we could put into this thing. We can find out how, what's the radius and what's that gravitational constant. We know that for the moon. We know what the radius of the moon is approximately, and we can fill those values in, and then it'll kick out something basically that we need to know about. How do I get that satellite to quit just circling around the moon, right? Probably more typically used around Earth. And why I brought up another thing is, the gravitational constant is based on Earth, so that would end up being 1 most of the time. Well, let's solve this formula. And in this complex deal, now at least we don't have the sub numbers, but we do have exponents and stuff like that. So first thing they do is clear the fraction. So what I look at this, I have 2 fractions here. I've got R squared and R plus H. Well, the easiest way to do that is the LCM is those 2 things multiplied together, because they really are prime in a sense. We can talk about what prime means some other time. That should be reviewed too. Well, by multiplying, here's that LCM, or least common multiple, or the thing that's going to clear my fractions, right? I know that if I take this and multiply it by both of these fractions, I'll end up with not fractions. That's another way to say that. So they multiply and they clear the fractions, and they end up with this right here. Now removing the factors equal to 1, we have some things like that where I look for things where R plus H over R plus H is 1, and those kinds of things. So that's what they're talking about here, is that simplifying some fraction stuff. Okay. Now remember, when you're solving for H, they're looking for H, which again in the definition, H means the height above the planet. We're going to distribute the v to the 2 power, since H appears to only to have a factor of R plus H, is easily divided by both sides by v to the 2nd power. Okay. So in other words, they're solving for H. So I'm looking at this thing. Well, H is in this quantity, so let's get rid of things that are going to have order of operation issues around it. So I could multiply this. If I distributed this v squared times this quantity, now I got 2 terms with the h value in it. Okay? Well, let's just not do that. I mean, I can, as long as I follow the rules, they took 1 over v squared times both sides, or they say dividing by it. I'd say the reciprocal of that again. I'm about to quit saying that over and over. But, well, since that is 1, that's why we did that. I end up with this new equation, equivalent equation. Now it's getting easier to solve for h, right? So I add a negative r to both sides, or subtract r, and I end up with h equals 2r squared g all over v squared minus r. Now, what I have is a new formula, basically, to give me the height of the satellite if I know these other variables. I can put it in. This third example is the acoustics, the Doppler effect. Here's the formula. If you've ever heard a train go by when it's blowing the whistle, the frequency of the horn changes. In this case, they're showing us a ambulance. They could have a steady tone going on, and you get a Doppler effect, that's called, where when the vehicle is moving towards you, you get a different sound. In fact, the frequency seems higher, and then as it goes by, it goes lower. This is a pretty good illustration of frequency. If frequency, what our ear hears really is just compressions that happen on our eardrum. So as that ambulance coming for us here is getting pop, 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 pop here, this frequency, or the amount of little pops on that eardrum, this is a time model. So the space between them is smaller, right? So you get more hit, more pops on your eardrum per second, which is a higher tone, is the way we perceive that as it's coming towards you. It's kind of like it gets compressed because the sound really has a speed. You have the speed of sound. Well, when you have a speed of a vehicle going with the speed of sound, it kind of catches the sound as it's going in a way, which is definitely not the right proper terms to do that. But this is the effect that happens. And then as the ambulance goes by, it sounds like the siren actually went down in tone. You get a lower tone because what's happening now is there's getting more separation between those compressions on your ear. Well, that's a Doppler effect. We hear it a lot. This is a formula that actually works to determine some stuff, where F frequency is of the sound that is moving at a velocity v. Here I'm kind of locating them in the formula. Here's v, and this g thing they're saying is towards a person who hears a sound as g. So the sound of the frequency of the sound coming at you. So if you had a tuning device that could measure frequency as that ambulance is coming towards you, you can take that frequency, and what you're hearing as it's coming towards you is a frequency g, and here's the speed of sound in the particular medium. That's another variable. We think about speed of sound being a constant. It's really not, because it depends on how much moisture is in the air, those kinds of things. What is the air pressure at the time that's happening? Those actually affect the speed of sound. So we're going to find the speed of sound in this particular medium. So we want to find out, we could take these things and basically we could find out what the environmental issues are basically affecting speed of sound at that given point, if we know these other things. Okay? So same process basically, and they're going to give us a box here down below that basically says, clear the fraction, solve for the variable is really what we're doing. This should be review. Just the complexity of it has increased quite a bit, is why they wanted to show you these examples. And these are really good to go through. It's very good to do your assignment through this stuff, because it is really going to test to make sure you understand your algebra skills in solving for certain variables, for sure. So they go through that process again here to solve for S. Now I got a new formula, basically a new formula, that will give me the speed of sound in that environment that I recorded those variables at. So that's basically what it goes. Clear the fractions, use the LCMs, remove parentheses if necessary, do the multiplication. Like one of the things with that velocity squared, maybe you don't need to. You can basically keep solving, and not have to distribute, especially if inside the parentheses is the variable that you're trying to solve for. Factor out any specific variable if more than one term, so look for the distributive property, factoring issues, that kind of stuff. You're going to simplify things. Multiply and divide both sides, isolate the specific variable, right? Solve for that variable. Alright, now we're going to talk about variation. There's a couple different kinds of variation that we're going to talk about in this little section here too. And again, it comes back to this relationship. And they're trying to get some real world stuff that you probably, you're used to hearing about or being involved with. And the first one we're going to go through is direct variation, and then inverse, and then combine. Well, direct variation, they give us this example of a fitness trainer who earns $22 per hour. In 1 hour, then $22 is earned. In 2 hours, 44, 3 hours, 66, and so on. This gives rise to the set of ordered pairs, which is, we should say, oh, I got ordered pairs. I could even write an equation. If I know it's linear, I could make an equation out of these ordered pairs by getting the slope and use point slope form and so on. Chapter 3 stuff, if I got it remember right. Well, they're not really going there yet, but we'll go. With this stuff, we have a ratio of our earnings, E. They're talking about E is earnings. They define this variable. It's very good to look at that so you know what you're looking at when you're going into formulas. And T is time, in this case, time recorded in hours, right? So 1 hour, 2 hours, so on. If the situation is modeled by pairs for which the ratio is constant, we say there is a direct variation. Here, earnings vary directly as the time. So we have earnings over the amount of hours you work will equal to 22. So in this case it would be, like say, oh, I made $66. I worked for 3 hours. Yeah, I got $22 an hour, right? Well, we can also solve that for E, earnings, which is usually what we look at. You say, hey, I make $22 an hour. If I work 10 hours here the next 2 days, I'm going to make $220, right? Well, that's usually what we do here. What are my earnings going to be? Well, here you know it's a constant here of $22 per hour, and then it's just a matter of how many hours did you work. We can also again put this in function notation, where the earnings function over time, I'd plug in time t here. I would take this output model here. This machine basically takes 22 times whatever number I put in for time. Okay. Well, that's a direct variation, and they're going to start talking about some terminology and those kinds of things. They bring in variables, like going back, M was something they used for slope, and B was in the point in the slope intercept form. B was the y coordinate of the point that was on the line that crossed the y-axis, or in other words, x was 0. Well, let's read this. When a situation is modeled by linear function of the form f of x equals kx, or y equals ks, there is k, where k is a non-zero constant. We say there is a direct variation, that y varies directly as of x, or that y is proportional to x. Proportional comes back to basically equal fractions. Proportions are equal fractions. I don't think I've ever talked about it in this series of class, but that's what that means. The number k is called the variation constant, or or the constant of the proportionality. Okay. Now, boy, that would be gibberish if you didn't stop and start defining some words here, right? So do that. I mean, don't bypass this stuff. You're going to go say, well, I could probably get through most of this assignment with no problem at all without being totally sure what proportional meant. But if I run into these kinds of things, if they have them in a box and they define them, it may not be exactly really crucially important for this assignment, but it's important in algebra. That's why they do it that way. And these are pretty common relationships that happen, or variations that happen in the real world. It says also note that k is greater than 0 for any equation in the form y equals kx indicates that such as x increases, y increases as well. Okay? So find a variation constant. We're looking for that k value in a sense of the equation variation if y varies directly as of x, and then they give us a relationship. Here y equals 32 when x is 2. I get an input of 2, and here is my output function would give me 32. We can put that in an ordered pair, and it's good to understand that this is the range and this is the, excuse me, I said that backwards. This is domain and this is range. The input's domain, the output is range. So I end up with this ordered pair 232 is a solution. Basically it says what they told me here, this ordered pair is a solution for y equals kx. Now how did they know this y equals kx? Well, it told me that there's a variation constant and an equation of the variation. Basically it gave me the definition of this type of variation. Okay? So I can plug these values in. I take the formula that they give us, or this form in a sense. Well, in this case the y is 32 and the 2 is x right here. So I end up with 32 equals k times 2, or 2k, and I solve for k and I get 16. So the variation constant in this case is 16. In other words, the equation y equals 16x is would basically, if I wanted to do the line of that, I'd have a line of all the values. You could do that. You could make a chart with, when you're getting paid by the hour, you could put a chart here and you could whip down a chart and go, what happens when I get 40 hours, how much would I get paid? And basically I'd go x is 40, I'd go to the line of this graph of my earnings, and it would give me an output value for the y coordinate. So I wouldn't have to calculate it, I can basically pull it right off the graph. Now example 5 is about ocean waves. I like this part here because they're not really giving you a formula, they're not giving you the algebraic terms for it, they're just saying here's the deal. Well, then you have to basically create this environment in algebra. You're interpreting this English language into algebra. And that's what it says here, familiarize. Because the phrase v varies directly as t, we can express the speed of a wave in miles per hour as a function of the swell period t in seconds. Okay? So in other words, they're setting up, how do I put this into a function? How do I interpret this into algebra? So they say thus the velocity of swell period time equals this constant times time. Okay? They use that k again, representing constant. So we translate that basically. Familiarize, read it, what am I talking about, what is this stuff, and all those kinds of things, and what did they tell me? What can I do with that? Translate that into algebra, you end up with something like this, v of t equals kt. And then I have some values I can pull out of here. It says knowing the waves swell at a period of 12 seconds are traveling at 21 miles an hour. That's two of my variables in this case. I have my output of 21 and my input of 12, right? Well, so 21 has to equal this constant times 12. Well, I can solve for 12, I get 1.75. Now to carry out, to find the speed of waves with a swell period of 20 seconds, we can then compute this. I basically have a new function that they created. You put t in there for swell time and the period of time of 20 again. So, and we end up with 35, right? So it comes out with the output. To check, make sure these things work and make sense, and you're off to the races into Functionville. Okay? So inverse variation is when things go up on the x, they go down on the y. In other words, if I was talking about slope, I'd be talking about negative slopes and stuff to tie it into some older information that we've gone through. Well, this inverse relationship is like this. So here, if you look at the ordered pairs, which is a good thing, here I get 20 input, I get 1. If I go 40 input, I get a smaller number, 1/2. 60, I get 1/3, and so on. Okay? Well, this relationship, we end up with a function that looks like a fraction, and they talk about inverse variation. So, and the situation is modeled by a rational function in the form f of x equals k over x, or y equals k over x. The k has to be a non-zero constant, or you just end up with 0. We say this is an inverse variation. Y varies inversely as of x, and y is inversely proportional to x. The k, number k, is the variation constant, or the constant again of proportionality. Note that k is greater than 0, and so on. Well, in this case, the same math, now they're just talking about fractional values, but you do need to know about these types of variation for sure. Okay, so they go through a couple word problems here, and then what happens if we have joint variation or combined variation, those kinds of things, and they address this and they call it joint, and so on. So like in this case, here's a formula for the volume of a right circular cylinder, or something that looks like a can. You could use this, you could measure stuff, and you could get the volume of that can. And that's what big V represents. Pi is represented by symbol, because it's an irrational number. I can't write that as a exact fraction. So they use that pi symbol, and then usually you say, what are you trying to find out? What degree of accuracy do you need to use for pi? Can I just use 3.14 as an approximate pi? Is that close enough? Or if it was something real scientific or something like that, they might go out 50 places past the decimal with 3.14159 and so on. It goes on a long ways. I can't remember. I'm not sure how far they have the digits out yet, if they're still working on that. There's a whole science of mathematics could be created on if they could figure out what the pattern of some of these numbers are, which they haven't done yet. Might be the key to space travel or time travel, or maybe my guess is that quantum physics is gonna break into some of those arenas mathematically, but I don't know, just guessing. That's me trying to write a science fiction book or something. I don't know. So joint variation, it varies jointly as x, but to finish this formula, you have pi, and then this is the radius squared times the height of the can, or this circular cylinder. Okay, and we say varies jointly as h and the square of r. Okay, in other words, the volume, if you change the radius of the can, of the circle, it's definitely going to affect the volume. Or if you change the height of this can, it's going to change the volume. And both of those have an effect on that. Okay, so they go through some other mathematics and equation solving and stuff basically on that. And I think that's all I'm going to say about those things and finish this up. This is the last section of the chapter, so we'll have a review assignment after this. So there's no new video. There'll be a review, and then we'll have a quiz, just one quiz that you'll have 3 attempts on. And what I want you to do with those quizzes is that you attempt this material without additional resources, because the next thing after this quiz is a test on the chapter, and it will be proctored, so it would be a good time. We're talking early, hopefully the end of this week when I'm doing this video anyhow, to have a chapter test which needs to be proctored, and which you can arrange with look through proctoring services on the Wenatchee campus, or there's proctoring service at the OMAC. If you're somewhere else where you can't get to those campuses, you need to arrange a proctor in your area and get that information to me so I can get the test to them and they can proctor that test for you. But the quiz, again, you get 3 attempts at that quiz. I take the best score out of the 3. So I would use it as a learning tool. I'd want to have a good grade on one of the 3, which will probably end up being the last of the 3. But I'm not going to stop taking, if I'm not sure of the material, I'm not going to stop from taking the first attempt, because I want to see where I'm at. It'll tell you what you get wrong and those kinds of things, but it'll hopefully help you get a good idea what you may need to study more before you do another attempt, and more importantly, before you take that chapter test. So talk to you later.